Hello. Good afternoon. Welcome to Welcome to Science Sundays. My name is John Beacom. I'm from physics and I'm representing physics and astronomy, but I'm also representing a broad committee from across the College of Arts and Sciences that prepares these lectures. And those committee members include people from the natural and mathematical sciences and the social and behavioral sciences, and you'll be surprised to learn maybe it also includes people from the arts and humanities. And today's speaker was recommended by one of my colleagues in ACAD, which stands for the Advanced Computing Center for the Arts and Design. Apparently I got the acronym right. And so what we do, as you've heard me say before in the arts and sciences, is try to enlarge the scope of human knowledge. And we do it across all of those colleges, and that's an important thing that we do. But the other important thing we do is we try to share what we've learned. Knowledge for itself is not valuable, knowledge shared is. And so we do that in our teaching by trying to bring our students a world-class education closely connected to research and scholarship. And we do that through our outreach, like we're doing here today. And this and other events, we're trying to bring the fruits of scholarly inquiry directly to the public. So our speaker today is Kalina Borkiewicz. She did her undergrad and master's degrees at UIUC in Illinois. And there she had a job at the National Center for Supercomputing Applications, and she rose to be the director of Advanced Visualization Lab and the director of the Visualization Program Office. At that point, she quit. And she went to pursue a PhD degree at the University of Utah, where she is now a graduate student. And I think it's computer visualization and computer graphics and data visualization. Now, the other thing to remark is, besides being a pioneer in her field, and us being very happy that she's here today, she really went the extra mile to get here. How many hours were you stranded on the tarmac last night? A lot. It took her 25 hours to get here from Utah. So she really, really wanted to be here today. And I can see that there's a big crowd here today, that they really, really want to be here today. So let's welcome our speaker. Thank you very much.
Hello, everyone. Thank you so much for joining me here today. I'm going to be talking to you about data visualization with a Hollywood twist. And as mentioned in the introduction, I did spend the last 10 years working at the National Center for Supercomputing Applications, NCSA. And even though I'm not there anymore, a lot of the work that I'm going to be showing today is from my time there. So I just want to give credit to that institution. Let's proceed. The key phrase in my talk title is data visualization. If you've heard this before, you might be picturing something like this. Bar charts, scatter plots, X and Y axes, data analysis. This is a common type of data visualization. It is not the type that I'm going to be talking to you about today. The realm of visualization can be broken into several categories. The first category is called information visualization. This includes pie charts, bar charts, the type of stuff that was on that previous slide. This type of data often comes from spreadsheets and can represent things like sales data, the stock market, social network connections, often abstract concepts. But there's another category, scientific visualization, which is kind of an entirely different ballpark. It involves visualizing phenomena that actually exist and take up physical space. The stock market doesn't take up real space, but something like the planet Earth, a galaxy, a tornado, a molecular structure. These things fall under the category of scientific data visualization. Within that, though, we can break it down further. The more Common type is traditional scientific data visualization, where the focus tends to be on data analysis. Here I'm showing a video created in this style of two planets colliding. This is a simulation that was run by scientists on a supercomputer. Color here represents temperature, so as the planets collide, things become extremely hot and turn red as the planets are liquefied and vaporized and mixed together. By contrast, cinematic scientific visualization, which I'm going to be talking to you about today, focuses on communicating science to audiences who are not necessarily experts, audiences like you. So the goal isn't to analyze the numerical values of the data, as with traditional visualization, but rather to convey the concepts in a way that is interesting and beautiful and appealing and educational and can be appreciated by everyone. So here's the same data set, actually, of a planetary collision represented in this cinematic style. These types of visualizations are commonly seen in documentary films, in museums. Here's a sampling of movie posters that I personally have contributed to in my time at the AVL. These include IMAX films, television shows, things you can find on Amazon Prime, in your local planetarium, etc. I'll play a brief demo reel that shows off the work of the AVL team in just 90 seconds to give you a brief idea and glimpse of the type of work that this involves. Thank you. That wasn't all just me. That was an entire team's worth of effort. So I'll share that applause with the others. So cinematic scientific visualization really focuses in equal parts on the science, the art, and the technology. Putting all of these things together actually requires quite a complex pipeline. I'm just putting this up to kind of show you at a high level some of the steps required to create this. Not going to cover this in detail. I'm going to simplify this as saying that creating these visualizations requires solving 3 types of overlapping challenges. And I'll go through these one by one, starting with design challenges. So first of all, what is it that makes a data visualization cinematic? All kinds of visualization, whether you're making a bar chart or this sort of stuff that I just showed you, requires thinking about design and answering some common types of questions, like how will you represent the data? What aspects of the data will you choose to highlight? Because you can't show everything. That's usually not possible. What colors will you use? Lots of questions like this. With cinematic visualization, we have to answer all of those questions, but there's additional considerations as well. Things that are more commonly found in the movie industry. So thinking about how do you design the overall scene? What path does the camera take through this virtual scene? What's the composition of every image in the video? I'm going to show you some examples of traditional visualizations compared with cinematic visualizations to really highlight this with some examples. So this is a traditional visualization. I'm showing this photosynthetic organelle called a chromatophore. And this is a visualization that the science team had made a couple years before our collaboration. And this was created by scientists and for scientists. So, it's kind of on a white background, so it can be plopped into a PowerPoint presentation. It's got some vocabulary on it that unless you're in this field, you're probably not familiar with. It's a little bit, maybe hard to follow for a more general audience. We wanted to tell this exact same story of, light hitting this object and starting the process of photosynthesis with the same data set, but we wanted to make it immersive and exciting and understandable to a general audience. So here's how we did that. We started out by creating a context. We made millions of copies of this chromatophore object and organized them into the shapes of the bacteria that they're found in. We designed an exciting camera move using our custom camera choreography software called Virtual Director, which we linked together with VMD, a scientific software for rendering molecular structures. We changed scales and we slowly increased the amount of detail that's shown to the viewer. So we don't just start by showing the data, we design an experience that includes cinematography, lighting, color, moving elements, and tells a story. So now we finally see a photon of light hit the chromatophore and the process of photosynthesis begins after all of that setup and introduction. The video that you just saw wasn't actually created in that format. We created it in an immersive format for a planetarium dome environment. So it's intended to be viewed in this kind of theater space where it's really wrapped all the way around you. I'll show the video to you again, this time in its native format, but you have to know how to interpret it. So I'll show you this type of circular image, and you need to imagine that it's wrapped all the way around you. So at the very bottom of that circle is what would be in front of you. At the center of the circle would be directly above your head, and the top of the circle would be behind you. So again, here's the final visualization now in this format, and including its narration and all of the final components that went together.
Scientists have sought to enter the world of primitive bacteria that thrived in hot springs almost 4 billion years ago. Using one of the most powerful supercomputers in use, they have simulated the chemical mechanisms that allowed these organisms to evolve and spread. These one-celled creatures behave like biological machines, powered by electrical charges and equipped with special sensors. They specialize in capturing the fleeting energy of sunlight. When a photon hits, it excites rings of chlorophyll molecules. The energy now held within these rings.
All right, I'm not going to play the whole thing, but I wanted to give you a taste of, what the final looks like with all the narration and added components. So now I want to show you a few examples of specific filmmaking techniques that we often use. One technique is what we refer to as putting the camera inside the data box. So something that you'll often see in more traditional visualizations is, an entire data simulation kind of in a box and seeing that box rotating around. This is a very common type of representation that I'm showing on the right. And on the left is a similar data set where we're placing that camera inside the box to get the viewer as close and personal to the data as possible. This really makes this feel more immersive and exciting and isn't as distracting as the image on the right because to a general audience, oftentimes showing the boundaries can be confusing. So here we're looking at the large-scale structure of the universe. Does the universe have boundaries? Sometimes these questions can rise in your head if you're presented with the information in this way, and that can detract from the story that you're actually trying to tell. One rule of thumb in cinema and in photography is called the rule of thirds. It turns out that humans find images more aesthetically pleasing when they're not aligned with the center, but with the 1/3 and 2/3 lines of the image. So here we've placed the Earth along one of these intersections. And even though at first glance you might think that the leftmost 1/3 of the image is wasted space because it's almost entirely black, this was actually a conscious decision for us to compose a frame that's more aesthetically pleasing. We often use lighting techniques to bring some dramatic flair to our videos. Darkness can add mystery and allows you to do a grand reveal of data features in a way that's more surprising and more impactful than just showing the data outright. One of the things that's really, really important to what we do is providing context. So I mentioned that in the earlier photosynthesis example. Here's another data set. Right now I'm showing this without any context. I want you to take a second and think about, like, well, what do you think we're looking at here? Now, if I show it to you like this, maybe it becomes a little bit more clear. We're flying over the surface of the sun, and then we dive underneath that surface to see rolling waves of plasma. And this is actually the main data set that we're trying to tell the story about, but we needed to provide that context to orient the viewer before we can introduce the data set. Here's a snapshot from this visualization a little bit later on that shows an X-ray view inside the center of the sun. Something that's very challenging about providing context is that it often requires combining multiple data sets. And each data set is in a different data format, comes from a different team of scientists, has its own set of problems. So I'm going to break down this image into all of its components. We began with a data set of solar surface convection by a scientist named Matthias Rempel. His data included surface magnetism vectors, which we showed as these spikes. The sun's surface was a simulation by Dr. Rempel that came to us as a series of black and white rectangular images. We tiled these images onto a sphere and mapped them like that, and we started playing each tile at a slightly different point in time so that you wouldn't see obvious repeating patterns. We then used a facing render layer based on where the camera is to make it more transparent to provide this X-ray view. Around the rim of the sun, we used photographic time-lapse imagery from NASA's Solar Dynamics Observatory, which is a space-based telescope that has cameras looking at the sun. We put the whole sun in the correct context, so now there's maybe difficult to see on this projector, but there's a starry background sky image. That's a photographic mosaic from Axel Mellinger. And finally, the interior simulation is by Mark Nish and Nick Nelson, which shows an important feature inside the sun, these spinning vortices around the equator that the scientists hilariously nicknamed bananas. And the reason for that is maybe more visible here. This is a visualization made by the scientists where you can see these kind of banana shapes. We also added rotating streamers around these bananas to really emphasize their motion, because part of the story that we wanted to tell is that these are rotating. And that was a key component of the overall story. So I'll play the final visualization for you now. I'll cut that short there. With that, let's move on to communication challenges. I like showing this comic to start off this section. I'll read it to you. There's a lecturer that says there's an eye at the center of a hurricane. And then you see 3 different interpretations from students in the audience. The first interprets it correctly. The second person thinks that there's a literal eyeball in the middle of the funnel of the hurricane. And the last student thinks that this is about the letter I, which is in the middle of the word hurricane. What's great about this is that it really shows that communication is challenging. Even a statement that you think might be, perfectly obvious and, as succinct and clear as can be wildly misinterpreted. People with different backgrounds, with different educational levels, different ages are all seeing these visualizations. And it's very challenging to create something that'll make sense to such a wide group of people. But it's not just that it is a challenge. There are actually some instances where it is impossible to show something in an accurate way. Let's take map making, for instance, to give you a concrete example. Sometimes it's not practical to show the Earth on a globe, and so you want a flat 2D map representation. The Mercator projection is probably the most common way to do that, and it looks like this. But it misrepresents the sizes of land close to the poles. So here's a nifty little web app that lets you drag around different countries and see what they would look like on different parts of the map. So this is not a very accurate map projection or visualization, is it? So let's try a different one. This is a different projection that solves that problem. Now everything on the globe is the correct size. However, you might notice that now Greenland is cut in half. So we've introduced a different problem by solving the first one. But surely we can solve both of these problems, right? Well, it turns out no. There are many ways to visualize the Earth in 2D, and all of them are wrong in some way. And this is not an exhaustive list. Here's just a small sprinkling of some of the ways that you can do that. So there often is a wide gap between numerical information, which might be accurate, and then how you can actually display and interpret and understand that information. Projection issues aside, maps are a great way to convey information. Here's a map that shows each state colored by which party took most or all of its electoral votes in the 2016 election. At a glance, it might seem America was split pretty evenly between red and blue. But it turns out that the amount of red ink on this map is not proportional to the amount of electoral votes that went to the red party. It's proportional to the geographic size of each state. So Montana, which is very large and adds a lot of red ink, represents only 3 electoral votes, whereas the relatively small New Jersey adds a whopping 15 votes to the blue party. So here's a recreation of the map that scales the size of each state based on how many electoral votes it got. And you can see a more accurate result of the election. We can do the same thing by county rather than by state. And now this data visualization tells a different story than just who won the election. This tells the story of how urban areas dominate the outcome of an election. Or maybe another narrative that you can tell with this is that people with very different opinions are living next door to each other and that the country is deeply divided, right? Well, no, not if we color by the strength of a party's dominance. So now that we've introduced purple, we can see that there's a lot fewer solidly red and solidly blue areas, and there's a lot of mixing that happens. So it should be becoming clear through these examples that data can be visualized in a variety of different ways to tell a variety of different stories. And it can be quite easy to spin a data set to tell the story that you want it to tell. Some visualizations are better than others for this reason. But you should keep in mind that every visualization you see, somebody has made a decision on what to show, what not to show, and how to show that. So if there's one thing you take away from this talk, maybe it's this. When you see a visualization, really think about it critically. These 4 images show the exact same colliding galaxy data at the exact same moment, but they have significant differences. In A, we're looking at just the stars in the data set, and we're emphasizing regions of new star growth. In B, we're once again only looking at the stars, but now we're adding motion blur to emphasize how these stars are moving relative to each other. In C, we're visualizing the stars together with the gas in the data set, and the gas is colored by the identity of its originating galaxy. And in D, we're looking at stars and gas again, but the colors are mapped to the destination. So all of those tell this different stories with the same visualization. Unfortunately, the story that you tell doesn't necessarily even have to be true, even if it's true to the data. So I'm going to give you a few seconds to think about what's wrong with this visualization. I'll give you the answer. The y-axis is upside down, which makes gun deaths seem to decrease when they're increasing and increase when they're decreasing. There's no way to know if the visualization creator did this maliciously because gun violence is a politicized issue and maybe they were trying to lie about it. Or maybe this was an honest mistake when somebody was just trying to create a unique graph that looks cool, because this does look like dripping blood. You know, it's kind of a neat design thinking about it in that sense because it's tied to the story. But does it matter what the intent of the creator was when this still gets put out on the news and seen by hundreds of thousands of people? So this is actually quite risky to put out information like that. So one thing that we very often do and make it a point to do for all of our projects is we work very closely with the scientists who are providing us with the data to make sure that they're involved in the iteration process and can validate that the decisions that we're making are conveying the data accurately. I'm not a scientist. My background is computer science, yet I'm visualizing molecular biology, astronomy, climate change. I'm not an expert in any of those fields, and I don't pretend to be. So we work with the people who are experts who can tell us that we're really telling the right story. We don't just talk to the scientist experts, though. We also talk to our audiences. We identified recently that sometimes our audiences have trouble telling apart the difference between a photorealistic data visualization or something that might have actually been captured as a photograph or a video with, say, a telescope. Or something that's completely artistically generated and made up. So once we identified this as a problem, we started doing focus groups and testing and surveys to make sure that we're able to convey this and other concepts more accurately. Let's move on to some technical challenges. First challenge is that big data keeps getting bigger. This goes for both data that's simulated on, say, supercomputers and also just captured from the real world. So here I'm showing the Vera C. Rubin Observatory, a telescope that's expected to be completed very soon, I believe, that will be producing 20 terabytes of data every single day. Here are some stats as an example of a data set that we recently worked with. That is a digital elevation model, which is a record of height of every piece of land north of 60 degrees, which is 1/6 of the entire globe at a resolution of 2 meters per pixel. It took the scientists 1.5 billion hours on the Blue Waters supercomputer to even process and assemble this data. So this is an extremely large data set. And we weren't working with the entire 200 terabyte data set for our visualization, just a measly 45 terabytes. But that's still a very large amount. And it took us 110,000 hours on a supercomputer to create our visualization as well. So these are kind of the scales that data can be these days. Another challenge is that data is messy, and it requires cleaning and processing. So here's an example where I've zoomed in to the data set of the Arctic from earlier, looking at just one ice cap that is collapsing. This data set was captured by a satellite taking photographs of the land, and an issue with satellites capturing data about land is that there's often clouds that get in the way between the satellite and what's being captured. So here along the top, you can see these messy patches that pop up, and that's where the clouds were incorrectly mapped as elevation of land in this data set. When reconstructing the data in 3D, you can see these giant spikes where the clouds are represented as land. This is obviously very problematic and not something that you can put into a documentary or in front of a general audience. So we were able to clean and process this data with a combination of algorithmic cloud removal, manual labeling, and machine learning segmentation. I'll play a video that goes into some of the behind the scenes of making this particular visualization.
Here's what went into making a piece of Atlas of a Changing Earth. We built on the results of the Arctic DEM survey project. That survey used high-resolution satellite imagery, hundreds of thousands of observations spanning several years, and measured the Earth's shape in fine detail, covering all the land north of 60 degrees latitude. Transforming that imagery into this mapped dataset of Earth's topography required millions of hours of Blue Water's supercomputer processing. Satellite observations were in strips, a few kilometers long. Throughout the survey, many areas were observed on dozens of occasions, revealing how Earth's topography changes with time. This shot from Atlas of a Changing Earth animates the multi-year Arctic DEM survey in the context of a realistic-looking Earth. The visualization incorporates seasonal changes in Earth's appearance. We created it in layers. On the ocean is a climate model simulation of sea ice coverage. To design the unbroken animation path around the world and into Vavilov, we used AVL's interactive Virtual Director software. Virtual Director shows a simplified preview of the scene in the correct 3D location. Final rendered elements fit right in. Datasets, camera paths, and so on are brought into the commercial software tool Houdini from Side Effects. Its node-based architecture supports a mix of programmable and interactive design. The DEM survey data shows exquisite detail, but contains many artifacts, thanks especially to clouds. Seen in a 3D landscape, every defect becomes even more prominent. Lots of manual work went into cleaning the raw survey data, masking out clouds and aligning strips with each other. The DEM data was observed at discrete times at irregular intervals, days or months apart. To give the sense of continuous motion, we used morphing interpolation in Nuke on the high spatial frequency ripples in the collapsing Vavilov ice to create three-dimensional evolving topography. Here's what went into that. Starting from a flat version of the landscape, we add the time-interpolated topographic relief and use Landsat optical imagery to provide color. It too is interpolated over time. Over wintertime darkness, we again alter the landscape color and lighting, and the sky, to suggest dim twilight. As springtime returns, so does Landsat imagery. The sun's very low as spring begins, so the early Landsat images are tinged pink with sunrise.
So another type of challenge that's related to the size of data, when dealing with data from the physical sciences, whether that's astrophysics or molecular biology, objects are often interacting with each other across vastly different timescales. So in the previous video, you might recall that we started out by looking at the entire Earth, and then we zoomed into this one particular ice cap. We actually did that in one seamless camera motion. This often leads to technical issues like floating point errors, and creative methods need to be taken to show both the large-scale and the small-scale objects simultaneously. Even though a single data set is not going to include something at the resolution of the Earth and also the entire observable universe, as I'm showing on this slide, we actually did create a single seamless visualization that combined all of these data sets, starting at the Earth, zooming out to look at the solar system, zooming out to the Milky Way, and zooming out to the large-scale structure of the universe. Lots of issues with relating to how to actually do that seamlessly, but this is a common problem with this type of visualization. Because data can be obscenely big, it's often not practical for scientists to capture or to create data at regular time intervals. So more data is often produced when there's something interesting happening in the data set, say here and here, and then less data is captured when maybe things aren't changing as fast or when there's nothing really that interesting happening. This results in data sets where time may not move linearly, which can't produce smooth-looking images without additional data processing. Here's a data set of a planetary collision that I briefly showed earlier. We received this data from a scientist, Dr. Knupp, at the Southwest Research Institute. And here's what it looked like before we put in any design work. Obviously, it's not very pretty to look at as just black background with white points. But aside from that, there are a few things that are concerning or troubling about this video. One is that it's over very, very, very quickly. So you kind of have to watch it on loop several times before you can really get a sense for what's happening. It just goes by way too fast. The other thing that's maybe a little harder to notice, but maybe once I point it out, you can see that the video seems to speed up halfway through. So why is that? Before I answer that, here's the final visualization that we made of this data set. We added lighting from the position of where the sun would be, which gives the planets depth and shadows. We added textures to the planets and a background of stars. We used information from the data, taking the type of matter and the temperature at each point to determine whether it should be a solid, a liquid, or a gas based on that information. When a point becomes hot enough to be a liquid or a gas, we also make it light up. Obviously, we also slowed this down by a lot. I believe it was by a factor of 20, to make it so that you can actually sit back and watch and enjoy it. And perhaps one of the most important elements that makes a video look and feel cinematic is the camera treatment. So we're revolving very slowly around the data, and once again, we're getting right up close and personal to it, to really make it immersive and to convey the large size and feel of these planets. Once again, this was actually created for a planetarium dome environment, which is more immersive, so you can kind of imagine this maybe being wrapped all the way around you. One of the coolest features is as this arm comes around, it kind of feels like it whacks you in the face in the dome. So we really wanted to make that, exciting and immersive and really getting up close to the data. So let's go back to the data and break down and fix some of the visual problems with the original data set. So with regard to timing, why does it seem to speed up halfway through? Time is going at 2 different rates in different parts of the simulation. This particular scientist is studying the initial impact, so wrote out more data at the beginning, less data at the end. So we needed to retime this to make it look smooth. So to fix time, at every point in this data, the simulation keeps track of different attributes. We took the time and the velocity. Since every single particle is going in a different direction at a different speed, we were able to keep track of the particles one by one. If we know where it is at time 1 and where it is at time 2, we can figure out where it should be at time 1.5. So doing this for every particle, we retimed and slowed down the simulation, so we got something like this through a process called interpolation. The next challenge is that there are many different coordinate systems that a data set might be stored in, many of which might not be understood by the software that we're trying to work with. So I showed this image before with the example of it being difficult to communicate due to there being these different representations. But it's also problematic from this technical standpoint. Because data can be represented in any number of different coordinate systems, we have to understand how to read those coordinate systems. It's not only true for maps, it's true for all spatial data, which comes in a variety of representations, and here are some of the weirder ones that I have come across. Another challenge is that there isn't actually any software that is intended to create this type of visualization. There's 2 different categories of types of software that we often pick and choose between, and each has its pros and its cons. So the first category is visual effects software. These are tools that are used by the Hollywood film industry. This is what the Marvel movies use to blow up New York and do all these kind of other effects that are not based on real science or real data. We like using those tools because they're created for artists, and they give us a lot of control over things like camera, over lighting, over things that are more visual, and our designers can really make things look and feel cinematic by using these tools. However, they don't understand any scientific data because they're not intended to be used for science. So the other category of tools is the scientific software. Unfortunately, these tools are intended to create more traditional scientific visualizations, which are meant for data analysis purposes. So you don't get control over things like designing camera and designing lighting. These tools do understand all of the complex scientific data formats, but at the cost of not really being able to make them look cinematic. So we use a combination of these tools and also built some of our own software to fill in some of the gaps. One of the custom tools that we use is called PartyView and is developed by Stuart Levy back at the NCSA. This is open source. You can download it and play with it yourself. But the intent of PartyView is to speed up what we call pre-visualization process. These data files can be very large and can take seconds or minutes to load a single time step. So what we do with pre-visualization is try to load in very little detail, just enough to give us a sense for the spatial scale and the information that will allow us to create kind of camera moves and figure out what we're even looking at. We use PartyView in conjunction with another tool called Virtual Director. And here's what that looks like. We use this for designing camera paths. So here we're looking from the view of the camera, and then we're able to separate from the camera path and look at it from the outside. So now you see it as a line in 3D space. We're able to turn on a television view so we can still see what the camera is seeing and then go in and edit that path. This gives us a lot of control for creating camera moves in a way that feels more performative. This is kind of how you would create a camera move if you were working with a physical camera and moving it through space. So we find this very helpful. We don't create all of our own software, though. There are tools that we often work with. Houdini is the main tool from the visual effects category that we work with. Here's an example of the Houdini interface, and we've loaded in a tornado data set. A little bit difficult to see, but with some custom C++ plugins and Python scripts that allow us to do pipeline and data conversion, we are able to load this data set into Houdini, and here's what the final rendering of that looked like. However, a problem with using tools like Houdini is that they expect data to be represented in a very simple way, like this grid on the left. The tornado data that I showed was represented in a grid that looked more like the one on the right. There's more resolution around the tornado itself, and less resolution kind of in the corner where there wasn't much going on, just maybe some boring clouds. This allows the scientists to really save storage space since they're not spending a lot of bytes on things that aren't very interesting. Another data format that has more resolution only where it's needed is called adaptive mesh refinement, and it looks like this, nested multi-resolution grids. Same concept, very different representation. Data can also come in spherical grids, or any number of other weird representations that don't easily convert into a nice grid like the one on the left. So when dealing with complex data types, we can force the data to fit into a simple grid by sampling it. There are several different ways of doing that, but trying to force one type of grid into another type of grid means that you either lose some data or that you end up wasting resources. But of course, we don't have to use Houdini. We can use different software. So let's take a look at a scientific tool. Just as one example, I want to talk about one called YT, which is a scientific analysis and visualization Python package. Like many software tools, YT can read complex data. So here's a data set represented in this nested multi-resolution grid format and what we were able to do with it on the right as the final video using YT. YT works in parallel and is installed on it was installed on the Blue Waters supercomputer. If you're not familiar with what a supercomputer is, it's kind of like what it sounds like. Very big, very powerful computer that's kind of like putting together thousands of regular computers. So we did that, and we worked on a visualization that we were able to render 16,000 hours of computing and do that all in one day. So the scientific tool really let us do that efficiently. YT is open source, which means that the code is freely available to anyone to look at, to modify as needed, which was very helpful to us. There's an active community that we were able to talk to and help add features and modify things to do exactly what we needed it to do. So if YT solves all of these problems, why isn't it our primary tool? One of the main issues is that it doesn't have a graphical interface. So this is not true of all scientific tools, but what is true of scientific tools is that they do often require some kind of expert to really even be able to know how to use that tool. In this case, the type of expert needed is a programmer. So there's no buttons for designing things, no sliders for modifying things. Everything needs to be done programmatically, which obviously does cause challenges because this is a very visual medium. Another downside with YT and with many scientific tools is that they often let you only visualize one thing at a time. So with this video, we're showing several things together. These cloudy features of the tornado, arrows going through it, a ground plane. Something like this would not be possible to do in a tool like YT. So something that we often do is we customize the tools. Taking these in particular, YT and Houdini have very complementary strengths. We want something that does everything here. YT does one half, Houdini does the other half. Nothing really solves all of the problems that we need it to. So to solve some of these problems, we created an open source middleware between YT and Houdini that I felt very clever naming YTini. This allows us to keep doing the bulk of our work in Houdini, but uses YT as a data reader for complex scientific data types. So that summarized the different types of challenges. Hopefully that gives you an idea of the sort of work that goes into creating these visualizations. With my last couple of minutes, I just want to tell you a little bit about the impact of cinematic visualizations. You've likely heard the phrase, "a picture is worth 1,000 words." And in case you never visualized 1,000 words, here's what that looks like. I would argue that these visualizations are worth more than that, though. Consider that these visualizations are included in museums. As one example, here are images from the Museum of Science and Industry in Chicago, where AVL's visualization of a tornado is part of a permanent exhibit called Science Storms. This museum gets 1.5 million visitors every year, and even if only a fraction of those stop by this kiosk, that's still reaching hundreds of thousands of people every year. Several of our science documentaries are available on Amazon Prime and other streaming services like Magellan TV, where they reach lots of people. A lot of our visualizations are available on platforms like YouTube. One of our distribution partners has a channel called Space Rip, and here you can see just one of our videos has 3.4 million views. So it's just incredible how many viewers this can inspire. Our visualizations often pop up on Reddit and really other very surprising corners of the internet. A really weird one is one time our visualization ended up as a backdrop in the movie Annie. It wasn't used in any meaningful scientific way, but still just a really cool random thing. But the impact goes beyond just cool little Easter eggs. We created a series of visualizations for a film called Solar Superstorms, which talked about the damage that we would get on Earth if a coronal mass ejection, which is an explosion on the sun, would be pointed in our direction. And this actually happened in the 1800s. We were invited to show our work to members of the United States Senate in Washington, D.C., before there was a vote on funding space weather research. And I'm going to take all of the credit for this, but that vote passed the Senate unanimously. The documentaries don't just impact people in the United States, they have worldwide impact. In the 2 years since its release, our film Solar Superstorms was translated into 12 languages and seen by millions of people. And this movie is actually available here at the Arns Sletback Planetarium at The Ohio State University. So if you're interested in checking it out yourself, please reach out to them to schedule a viewing. One last shameless plug. There's only so much I could talk about in 45 to 50 minutes, but if you're interested in learning more about cinematic data visualization, there's a 4-week course available on Coursera. And we also just put it up on YouTube on the Advanced Visualization channel, Advanced Visualization Labs channel, so check it out there if you want to learn more. So thank you. I'll take any questions now.
All right, let's have some questions. Let's see, I can't see anything yet. Well, okay, I see a lot of things. But rugby shirt guy.
What are the pros and cons that artificial intelligence can impact this field?
So the question is, what are the pros and cons of artificial intelligence impacting this field in the future? A pro is that it's not there yet, but I expect that it could help with a lot of the data processing steps at the beginning of the pipeline to really streamline, remove data artifacts. I did mention using machine learning to help with some of that in our processing. I see that as being super helpful in the pipeline. A con would be that it might become way too easy to create images that look like they're scientific data visualizations, but really aren't. So the issue of miscommunication to audiences, showing something that's completely fake and made up, but still looks real and scientific. Not sure what the solution to that would be, but that's certainly a possible problem.
Straight back.
Do you continue to work with AI so you can transfer your craft to AI and make it more legitimate and enabling you to see off into the distant future for the next evolution of your craft?
So the question is, do I continue to work with AI to try to craft it in a positive direction and help with things? I haven't personally. I know that there is a lot of active research in this area in scientific visualization, but it's not something that I'm doing.
For those who are visually impaired, is there any way to take all this and, let's say, take a soft piece of clay or whatever and have that move around and morph into various pieces to try to get this across or not?
Yes, the question is about ways of communicating this sort of information to those who are visually impaired, who can't use their eyes to see this. And there's two different areas that this field is going for that. One is data sonification, which is taking these data sets and rather than converting them into images, converting them into sounds. The other is 3D printing. Even though that doesn't necessarily convey the time-evolving aspect of it, since with our current technology, there's no way to create something that evolves over time, but you can still create a 3D representation of a data set so that somebody can feel it with their hands.
Go ahead, sir.
Yeah, in all your tables, I didn't see any reference to the software language R. Is R used in this process at all?
The question was about the R programming language and whether we use that. A lot of people that do data visualization do use R. I'm not aware of anybody that does cinematic scientific visualization using that language. There probably are people out there, but Python seems to be the more preferred tool.
Go ahead, sir.
Can we visualize higher dimensions than 3?
The question is if we can visualize higher dimensions than 3. I'm going to give kind of a cheating answer in that we do. Time is a 4th dimension, and we do often show that. Different variables in a data set are also additional dimensions. So if we're showing temperature together with energy, together with matter, that is visualizing multiple dimensions. That's not the answer you're looking for. I think you mean like these kind of cubes that have multiple dimensions. I don't know. That's not something I've explored. Seems like an interesting area of research.
Go ahead, ma'am.
So with the data and the interpretation, what level of artistic element are you incorporating? Because it's not just AI, there's people behind it. So taking all that data, how much do you feel you're using your own artistic efforts when you're creating that visualization?
So the question was about how much artistic effort goes into creating these visualizations. The answer is a lot. I kind of spend a lot of time talking about the challenges of communication and how you can visualize a data set in any number of ways to tell any number of stories. We do spend a significant amount of time, the artists in our team, kind of designing different versions and iterating and making artistic decisions on how to represent that. That's a very key part of our process. Really a lot of time is spent on that. It's a very important part of it.
Okay, last question. Go ahead, sir.
Yeah. So how much computer
the question is, how much computer memory do we work with for all of our work? I'm not a hardware person, so somebody else has always handled the hardware purchasing and specs. We do have high memory machines. What that means, I'm not too sure myself. You know, kind of a lot more than you would just get in a standard laptop. We do often render things on like a supercomputer where we have access to even more powerful machines, but there's kind of a two-step process. Everyone that's working on the team in the visualization has their own like personal machine that is kind of maxed out on specs with a lot of memory. And then there's the supercomputer, which has like even more. So as we're working on a day-to-day basis, we're kind of often working with smaller versions of the data, and then we send it off to the supercomputer to do the final heavy lifting. But sorry, I don't know numbers off the top of my head.
Okay, so as usual, a question for you. Would you like to have a cookie and meet the speaker? If so, please join us in the traditions room, which is just upstairs. Let's thank our speaker. Thanks.